Hi, my name is No Rhodes, and today I'm going to be talking about wildfire risk mitigation in power systems. This is work conducted by myself, Noah Rhodes, a PhD student at the University of Wisconsin-Madison, my advisor, Professor Lena Rold, also at the University of Wisconsin-Madison, and our collaborator, Professor Luis Ntaimo from the University of Texas A&M. I'll be talking about some of the motivation behind this problem, what is wildfire risk, and mitigating wildfire risk in power grids, and then introduce the optimization problem that we devised, the optimal power shutoff problem, and finish by talking about our case study on the RTS-GMLC system. The main motivation behind this problem has been a number of the deadly wildfires that have been started by the power grid in the last couple of decades. Recently, the 2019 Kincade fire in California, as well as the deadly Camp Fire of 2018, both started by Pacific Gas and Electric equipment. There's also one of the Black Saturday fires of 2009 in Australia, which is also started by components of the power grid. There are many ignitions that can occur in the grid, and especially in California, a lot of this has been the result of an increasing regions that are designated as high wildfire risk. In 2012, just 15% of Pacific Gas and Electric's service area was designated by the California Public Utility Commission as having an elevated wildfire risk, and today it's more than 50%. With wildfire risk, there are many different metrics and many different maps that are created by different federal agencies or state agencies. These all represent different factors, such as the likelihood of an ignition starting a fire, or the likelihood that a fire, if started, will spread to 100 or more acres. These are all important metrics for understanding wildfire risk in general, but it's not necessarily clear exactly what's the right kind of assessment for the electric grid. When we think about wildfire risk, there are three main parts that we consider. There's the probability of ignition occurring, there's the size and intensity of a fire that might come from that ignition, and then there's the damage caused by that fire, damage to both people as well as the infrastructure. When we consider these aspects, the utilities really only have control over one of them, which is a probability that some of their equipment might have a fault that leads to a spark that can cause an ignition of a wildfire. So this is the main aspect that we want to take a look at as to how utilities could change this likelihood. There are some long-term solutions that utilities could do, but these are in the range of months to years. There are some more short-term mitigations that we try and take a look at. In particular, we're looking at the public safety power shutoffs, which were used in 2019 to help mitigate the wildfire risk that PG&E had in their in their power system. According to PG&E, they found in 2019 100 instances of damage to their power lines, which might translate into 100 potential wildfires that were avoided. However, it's important to note that this is a trade-off because approximately 3 million people lost power, some of them for several days. And it can become a question of, was this 100 potential wildfires avoided worth the loss of power for these 3 million people? Moving on, I'm going to talk about the optimal power shutoff problem. The problem here has the objective function where we explicitly have this trade-off between the energy that is served in the system and the wildfire risk, trade-off between these two terms. And then there are some additional constraints related to component relationships, to the generators, and to the power flow in the system. This optimization problem is a mixed integer linear program where we have binary variables representing the component deactivation, as then we have a linearized approximation of the power flow equations, which is the DC power flow. The objective function here is the most important term, which is this trade-off between the total energy served and the wildfire risk. This total energy is a sum of the weighted demand at each node, where the demand can be prioritized for emergency services, for customers that need electricity, for medical equipment, or some other aspects. While the energy served is being maximized, we then minimize the amount of wildfire risk that is in the system, where the wildfire risk is the sum over all of the different risks of the components in the grid, and each component's risk is based on the wildfire risk in the region where it's located. or 0 when that component is deactivated. And then this alpha is the trade-off parameter between these two parts of the objective function. If alpha is 1, we focus completely on wildfire risk mitigation. This would involve turning off the entire grid just to reduce the wildfire risk because we do not care at all about energy serve. Instead, if alpha was 0, we don't care about wildfire risk and we just operate the grid to serve demand. You can think about this as the normal daily use of the power grid. The correct answer here is probably somewhere in between, but again, this trade-off is not clear exactly what the correct answer is. And I'll be talking about more of that later in the solution. As for the constraints, we have some constraints related to the component interactions here. These constraints listed show that if a bus or substation is disabled, then the connecting components to that substation must also be disabled. You can't serve load at a substation that's been turned off. And similarly, you can't have a generator or transmission line being attached to a substation that is turned off. We have constraints on the generators. Here I show the sort of a standard power limits on a generator, but that we also multiply them by this binary variable CG, where if CG is 0 and deactivated, then the power output of a generator must be constrained to be 0. The first section here is the DC power flow equations on the transmission lines. With an extra term, this big M value of theta max and theta min, big M value on the voltage angle differences between the lines. We need this in order to decouple the power flow in a line from the voltage angle differences when a line is turned off. The third equation is similar to the generator power limit equation, where the power on a transmission line is within its limits unless the transmission line is turned off, in which case it's constrained to be 0. The final equation is the power balance, which must hold at every single bus in the system, so that the total generation, demand, and power flow on lines through a substation must sum to 0. And we combine these together and we get the full optimal power shutoff problem. We compare this against a threshold heuristic, where if the component risk exceeds some risk threshold, then it is disabled. We have two different types of risk thresholds that we are taking a look at. One of them is this area risk threshold, where if the total risk within some predefined area of the power grid is above a threshold, all components in that area are disabled. And the second one is a transmission line risk threshold, which has an individual risk threshold for each transmission line. That is to say that each transmission line is the same risk threshold, but we consider all transmission lines individually. If they exceed the risk threshold, they are disabled. We take this set of components that are disabled and then run this maximum power delivery on the remaining system. You can think of this as an N-K outage maximum power flow, where we have a lot of outage components and we're just trying to find a feasible power flow for how much energy can flow through the system. We do this to estimate how much energy you could serve with these heuristic solutions. We study the RTS-GMLC 123 system to take a look at our methods. This is a grid that has geographic coordinates located in Southern California, and the wildfire risk is loosely based on the October 2019 California wildfire risk, where in the Western region, region number 1 has some risk for many of its buses. Region 2 in the bottom right has, in the top right has no risk for any of the components, and region 3 in the bottom right has some risk on some of the buses. The device's individual risk is estimated based on its location in this grid, and for transmission lines, the risk is averaged across the length of the line and scaled for that length. When we take a look at the solutions to this, we take a look at this Pareto front of the solutions. So for the optimization problem, we vary alpha from 0 to 1. For the transmission line risk heuristic in orange, we use different values of a risk threshold. And for the area heuristic, there was really only one solution here to turn off all components in this super high risk part of the grid. What we can see here is that for the optimized shutoffs, it is always both lower risk and smaller outages or less load shed compared to the heuristic methods. And we can take a closer look at these two solutions here that we are calling the medium risk solutions. There's two solutions here that have similar amounts of wildfire risk with minimal amounts of load shed. When we take a look at these two solutions, you can see on many of the substations here the distinct difference. The nodes in green here are nodes that have no load shed at all. And in orange, there's some partial load shed, and red is total load shed. In the threshold system, you can see many of these, especially in the left portion of the grid, that have a decent amount of load shed because the transmission lines that were selected to be disabled did not account for the load that would be connected to them. Whereas in the optimized shutoff case, many of these lines were kept on, but you can see some disabled lines in another region of the grid on the bottom right that were more medium risk. So what we really see from this optimal power shutoff problem is that it maintains some of the high risk lines in operation, but more of the medium risk lines have been turned off. We can take a look at this plot that shows the power transfer across a line versus the risk of the line. And you can see two of these lines here that have a decently high risk, but are still kept on because they transfer a lot of power across them and are still valuable to serve load despite the high risk. So based on the trade-off value, it's still worth keeping these lines active. One final thing to take a look at here is how well this problem scales. To do this, we took some additional cases, transmission line cases, and we randomly assigned risk values to them 20 different times and solved all of these with the optimal power shutoff problem. And what we can see is that most of the time, these solutions were found very, very quickly within just a few seconds. And this indicates that the continuous relaxation is tight. But there's some outliers here. For example, this case 89 one seems to be a pretty poor, fairly difficult to solve problem for the optimal power shutoff problem, where in the worst case, it took 21,000 seconds to solve instead of just a few seconds that some of the other cases took to solve. So it's not, and the continuous relaxation is not always tight. It would also be nice to see if at some point we can scale this up to a grid the size of the full state of California and try and understand what an optimal power shutoff problem would look like at that scale. In conclusion, we propose here a new method to optimize the trade-off of wildfire risk and power shutoffs. And our results show that accounting for the network power flow enables much better trade-offs than using heuristics that do not account for the power flow in the system. We also want to note that choosing a trade-off here is very challenging and affects many people. This is something that should likely be addressed by regulators and the public because their risk tolerance to wildfires and power shutoffs may not be the same as a utility. Thank you for your time.